So, we are still on false Swiss texturing, and we have covered material parameters and their influence, and today we will concentrate on process parameters. So, we had seen the effect of fiber chemistry, morphology of parent yarn, and physical and dimensional characteristics of parent yarn and their influence on the properties of textured yarns, likely influence. So, we come now to the process parameters. Process parameters are those parameters which we can control definitely. In the case of material parameter, if somebody wants you to texturize polyester, you can't help it. If they want 200 denier, then that is it. So, you know the influence of a total denier or denier per filament or the material characteristic, but you may or may not have much influence on the material. You may not be able to change. If there is a history that it was already drawn and texturized, drawn in heat set, then the crystallinity will be different, and because it will be different, then you have no choice except to understand if it is more, what you will go do, if it is less, what will you do. And how will you optimize? This is the way you will optimize, that you will choose some process parameter which you have complete control, and then based on the material you would optimize those. So, we still remember that we are talking about fully drawn material, all right, because one which is fully drawn behaves in different way, and that is what is our constraint at the moment. Of course, they are thermoplastic, thermomechanical, twist texturing and single heater machines, and the products based on single heater machines is what we are talking about. So, if you look at the process parameter, there are 4 T's of texturing: the temperature, time, twist and tension. So, you have a possibility of changing any one of these on the machine and therefore optimize the process. So, temperature, time, twist and tension, the 4 T's of texturing. So, what is thermomechanical texturing? It is a process, this sentence you may just try to remember. It is a process wherein stresses due to asymmetrical strains are released with some thermal stimulus. Asymmetrical strains, obviously different portion of the filament, different filaments within the yarn may not be strained to the same extent, and therefore, they are asymmetrical stresses, and these are being released, and therefore, the setting is because of release of energy. We have already seen the mechanism, and therefore, this is just one interesting part. So, first sentence we had already talked about that during this process, during this texturing process, there will be partial melting of crystallites and recrystallization. This would be required to facilitate rearrangement of molecules and also will involve stabilization. During this process also we can expect smaller crystals. If suppose there is a history of, let us say, heat setting or drawing, so some crystals may have been already formed. You can appreciate that all the crystals would not have the same size, same dimensions, like all molecules in a polymer also do not have same length or degree of polymerization. So, smaller crystals obviously may melt before and may also during this process coalesce into bigger crystals. The crystal structure may also change, which we said maybe if there are structures which are less stable, they may go into a more stable structure, and if there are crystal defects, they may get rectified during this process as well. So, the most important parameter therefore, is temperature, because all these things are going to happen at a temperature which is optimum for that material for texturing. So, temperature becomes an important process parameter. So, we talk about temperature of texturing. So, at what temperature should we be working on? This is very clear that if you have polypropylene, chemistry is different against, for example, the polyester, the nylons, and therefore, the temperature optimization would definitely depend on what material you are going to texturize. So, that will be, for example, the melting temperatures you are quite aware. Someone melts around 250 to 260, one melts at 215 to 220, the other melts at 170, and therefore, all the temperature that you will use for texturizing and optimization will be different, and therefore, temperatures are there. But let us say we try to plot rate of crystallization versus temperature. Rate of crystallization is also chemistry dependent. For example, when we said we have polyester which has got aromatic rings in the macromolecule versus nylon 6 which is aliphatic and more flexible versus polypropylene, they all have different rate of crystallization. So, even if we do not talk about the value of the rate, we can look at a generalized curve of rate of crystallization versus temperature. If we take any polymer, which now we are talking about thermoplastic material which melts, so you heat it up or you cool it from the melt. So, it is going to follow a certain uniform bell shaped curve, where at a particular temperature the rate of crystallization will be high. Let us say a temperature called T star, where the rate of crystallization is high. At some temperature, somewhere here, this may be the melting temperature, where everything is in molten shape condition, and so you cannot expect crystallization to take place. The kinetic energy is too high, molecules are vibrating, and therefore, they are coming together to either orient or coming together to crystallize is almost 0, because you said it is all molten. The other side also is a temperature which can be considered as the glass transition temperature, below which we believe the material, which is the polymer, behaves like a glass, means it is frozen, the vibration levels are very low, the molecules will not have enough freedom to do anything. All right. So, roughly all the materials like this would give a rate of crystallization curve with temperature, which is a bell shaped curve. So, it is clear that texturing temperature cannot be glass transition temperature, and the texturing temperature cannot be melting temperature also. So, it has to be in between. If somebody wants to ask what will be the texturing temperature, we will have to say something else. So, what do you think should be the temperature of texturing for any polymer? By looking at this curve, yep, T star, no, so not the T star. Anyone else would like to comment on this? So, I am just writing something. One option that has come to us is between Tg and T star. Other option was just above Tg. Any other option? There was another one also between T star and Tm. Okay, between T star and Tm. Good. So we have large range. We have covered everything. But somebody may like to understand why should you not do at T star? What are you likely to lose if the temperature of the polymer is actually at T star? What are you going to lose? Before this, let me just also say, if that at T star, if the value of the rate is, let us say, K star, so at K star by 2, you get a temperature which is also close to softening temperature. The material is still solid, but it is softened. So, there is no doubt that above glass Einstein temperature there will be an activity. Above Tm there will be no activity as far as the crystallization is concerned, but as you keep reducing the temperature, the opportunity for the molecules based on whether any kind of a nucleation is possible, they may start coming together. So, theoretically there should not be any reason for someone to say that I want any other temperature than T star, theoretically. Similarly, if you go above softening temperature, the difficulty levels may come that the material is softened and the individual filaments may start fusing with each other. So, they are still solid, but there is a compressive stress, you have twisted, there is a compressive stress, softened material, it may get fused. If some filaments get fused with each other, then our aim of texturing, which said that it is a twist free bundle of twist lively filaments, and we actually believe all the filaments are free to do what they want to do. If 50% of them can do something and the other 50 cannot do, then you will not get a better thing. So, one thing which can be we can be sure is that we do not want to go go above the softening temperature. So, why should we not be at T star, which is the rate at which this happens? There is no reason actually, except that we must be sure that actually you are at T star. What does it mean? When you say I am controlling a process parameter called temperature, what are we controlling? We are controlling the temperature of the heater plate if it is touching. We may have difficulty in measuring the temperature of the yarn at any given point in the heater. You can also appreciate that the yarn which enters the heater is at room temperature and its temperature keeps rising as it is moving in the heater, So, which temperature are we talking about? The yarn temperature or the heater temperature? So, if we are talking about heater temperature, then we actually do not have any measuring controlling device which is measuring the temperature of the heater and then saying, let us say we are at the optimum crystallization temperature. If this curve is true, so the polymer definitely will have the highest rate of crystallization. Highest rate of crystallization means the time required to finish the process will be less. Why should anybody not be interested in this? All right. But there is also an important factor that first we have no control on the temperature of the yarn, we only hope that this is it, this is going to be it at some point of time in the heater, because temperature is continuously rising. So, you have control only on the heater. Then the rate of transfer of heat from the heater to the yarn will depend on the difference in the temperature. So, as the temperature difference will keep on going down, obviously the rate of heat transfer will be slow. When somebody said we can have between T star and Tg, so you can probably get to that temperature, but which will always be less than T star. Is that true? So, you are actually designing an equipment saying, well, we will be below T star always, but possibly you should design an equipment saying that I will be likely to be near T star. And so, in a situation where the temperature of the yarn is rising from room temperature to a particular optimum temperature, we are wanting to set the temperature of a heater which would obviously transfer the heat, and that means its temperature should be higher than the expected temperature. If it is less than that, then obviously that expected temperature will never be reached. So, that does not mean a good design or an optimization process. So, if we look at the temperature of the heater, this definitely will be, so these things we are for the time being saying no, we are not happy with this. So, in some sense it will be between softening temperature and the T star. Generally maybe let us say this may be the temperature of the heater which we can control. How do we control? Of course, we like to measure some characteristics of the textured yarn and say, well, is good, is not good. If it is not good, then you would do something, take an action and then worry about it, but the control still is heater. So, one can say, well, oh, you are going at this point, therefore, the rate of crystallization is slow, therefore, the time required may be higher. Yes, that may be true, but it is much less economically burdening a little bit of extra time versus actually not reaching the optimum temperature. So, the optimum temperature of the heater will be near T star, above it, maybe 10 degrees above, maybe 15 degrees above, based also on what is the denier. If it is a very heavy denier, then obviously it is not just transferring of heat from the surface of the heater to the surface of the filament, it must obviously heat the inside of the filament also, inside of the yarn also. So, if it is a thicker yarn, obviously optimization may be different, have a temperature, but this will be optimized. And if you say, well, I exactly know every day, every time you come, you have given me polyester, 190 degrees or 195 degrees is the good thing, or 210 degrees is a good thing, is not fixed. So, if what is fixed is that you will try to optimize your heater temperature versus let us say one interesting property called the crimp rigidity. All right. So, based on the dimensions of the material and also the history of the material, your time temperature could be different. So, another question you may like to understand, and maybe you know it already, when does the crystallization occur? We said above melting point, obviously there is no crystallization. Before glass transition temperature, there is no crystallization. And what is our texturing process? Twist, set, detwist. And what is set? You have to heat, which we said we will heat, and after that we cool also. So, before untwisting, you have heating and cooling, right. So, if somebody says ki at what time or the part of a process the crystallization occur, heating or during cooling? Yes, heating and somebody said both. So, anywhere else? So, we see our curve, crystallization is happening. So, rate will keep going down as you cool, and you may actually go below the glass transition temperature we said. After that you will be safe, no more change can take place, and you may like to cool as much as possible, but we definitely must say that during both these processes crystallization can take place. During heating, decrystallization also takes place. Did we say that? You have to do partial melting. So, it does not mean that crystallization not taking place. There is a melting happening and there may be recrystallization also happening. This curve is wide and the melting is not taking place at one particular temperature only, it may start before, all right. But smaller entities are melting, it is not the whole fiber is melted, because when all the crystallites melt, it is melt. So, it happens during heating, it happens during cooling, rates may be different, and then we can get a textured yarn. So, that is the crystallization part of it, which is important. Randomness and disorientation will happen, but a good amount of stability, that we say dimensional stability, recovery from deformation, all those are going to be more governed by how much crystallization we have done. So, this good amount of crystallization, and that is how the fibers were also, the polymers were also selected for texturing, would depend on how much crystallization takes place after or during texturing, and it will help to make the crimp rigidity better and maybe stability also better under repeated loading, unloading, stress and recovery cycles. So, we come to the most important thing when we want to optimize any temperature or heated temperature, the effect of temperature on crystallinity, all right. So, we know something about rate of crystallization. So, let us talk about the crimp rigidity. You remember the rate of or the effect of development of crystallinity would also have something to do with the crimp rigidity, and therefore, let us first understand what would be the effect on crystallinity. Let us also appreciate that when we talk about variation in temperature, we would not be saying, well, I am varying the temperature from 0 degree centigrade to 260 degree centigrade in texturing. We already said below gas tension nothing happen, obviously. And then we also have a ballpark figure of what temperature of heater you would like to use. So, let us say you get yourself a margin of 30 to 40 degrees in which you will optimize. There is no point in getting a margin of 80 degrees to optimize, because then the experiments will be too many, all right. So, let us say without talking about a polymer, because this temperature will be different for different polymers, but let us say I am interested in measuring crystallinity. Texturing has been done, and after that I have taken it and measured the crystallinity, let us say wide angle crystallinity, wide angle X-ray crystallinity. So, what do you expect is the curve? Any guesses? How do we think it will go? Like this? Yes or no? No. Like this? No. And then this way? This also no. This way? Yes? Yes? No. Because unless and until you are going towards melting temperatures, going close to the melting, only then you can expect crystallinity to go down, because then the crystals that have been generated will also melt, all right. So, if we are looking at temperatures which are in the range in which material is softened enough, rates are high enough, crystallization can take place, and if we just recall as to what type of temperature that we are talking about, heated temperature, which is quite close to the rate where the temperature where the rate of crystallization is higher, all right. This is how. So, what do you expect then? The expectation will be that it will like to go and take up a curve, and rate of crystallization, rate of rise in crystallinity will keep coming down as the temperature is moving, because they are getting the highest values. After that the molecules may not have, they get jammed, and then getting more freedom from some other part of the molecule to come back and again crystallize, will keep on reducing. So, it will come to a state which may be quite jammed up state, and after that increasing it further will be difficult, because after the long molecular chain absolutely not free, it is held up somewhere else also, held up somewhere else also. As long as there was a possibility of chain folding, it could, but then after that it may not be possible. So, it is like jamming. So, as far as the crystallinity is concerned, it will start from the parent yarn, which may have whatever level of crystallinity. You can appreciate that a fully drawn polyester yarn may have crystallinity of the order of 25 to 28%. A fully drawn nylon, let us say, yarn may have crystallinity 35 to 38%, which has not been heat set, and a fully drawn polypropylene may actually be having crystallinity of the order of 70 to 75% or even more. So, are you getting the point? So, all the three fibers which are typical fibers are very responsive to texturing and the heat therefore, but their rate of crystallization are very high, and therefore, during preparation itself you can have a good amount of crystallinity generated, and during drawing also. And then you texturize. So, from that level it will go to whatever higher level it can go. So, it will go to a level and then stabilize unless and until you say, well, I am going to keep on heating till you melt. Well, that is it, but then there is no texturing. Even you can't go up to softening point, no melting there, but it is still bad because the fibers are going to get fused and get stuck with each other, which is not good, and that is so. So, generally in the range in which we will be interested in optimization, you will see the crystallinity rising of a parent yarn going up to a certain level, which depending on what can do. For example, in the case of polyester, you may actually go up to 55% to 60%, starting from almost 27%, which is quite a good amount of rise, and therefore, structure is becoming more and more stable. But we expect in this range this will not happen. Then we look at this value, which of course, the whole reason why we are texturizing is we want crimp characteristics to be improved. So, you remember what is crimp rigidity by definition. So, basically it is a recovery, how much it can recover and how much it recover after deformation, which is fully extended state of the fiber, right. We are not talking about fully extended state of a molecule, we are talking about a filament yarn. The crimps have gone when you put 0.1 gram per linear load. Molecules still are enjoying freedom, all right. Very difficult to orient all the molecules in any direction. So, that is the crimp rigidity part of it. So, let us see what kind of expectations do we have temperature and now crimp rigidity percent. You are now aware as to what is happening to crystallinity, all right. And then now we say what happened to crimp rigidity. Some guesses. Will the curve be similar to the crystallization curve? No. Okay. If it is no, then there must be some curve. Crimp rigidity rises like this? Yes? No? Okay. Then follows this curve? Yes? No? I can only see some heads moving, so I am just guessing. No. Then what? Yeah? Okay. This one? So, that means there is nothing. So, we will have to go to the lab and do whatever experiment have to be done. Let us say we want to actually measure, obviously it should rise. Do we believe that it should rise when we increase the temperature of texturing or no? So, it should rise because by increasing temperature you are going to be facilitating the partial melting. That is an important thing before crystallization. So, partial melting and then recrystallization, all right. So, when you increase the temperature, then the crimp rigidity should improve because crystallization is also going to take place. Possibly reorientation, rearrangement also has been facilitated, and therefore, setting is better. If setting is better, then you should expect that the texturing is better, means crimp rigidity should be rising. Its rate also should keep going down because you may not be able to increase the crystallinity, and therefore, more and more things may or may not happen. But it has been seen that the crimpacity can start falling after a certain temperature, obviously, which you will say, well, it did not appear to be bad temperature, why it is falling. So, you will stop somewhere there, and that is the time when either molecular degradation can become also a significant factor. You are giving temperature and time, and obviously this texturing is not being done under nitrogen environment. The environment is normal air environment, so there is oxygen. Anything that you heat in oxygen for a certain period of time, there can be, after a little work, you can stay, well, yeah, the crimpacity goes down. So, obviously, you at least have some reason to stop somewhere, okay, and this will happen much before the softening temperature. Sometimes in the case of polyester, it has also been seen that this polyester has crystallized quite a lot. It also has developed enough crystallinity, and therefore, when you untwist, there is a lot of resistance to untwisting, but machine is stronger than the fiber, and during this process people have seen cracks being developed on the surface, right. That means you are becoming so rigid and you want to do the untwisting, which is against the wishes. And so, beyond a certain point there can be degradation, there can be mechanical breakdown of surfaces, and therefore, because of rigidity, and therefore, much before when we expected that the crimpacity should go down, and any other reason which may fuse the fibers will also make sure the crimpacity is not good enough. And so, crimpacity would fall beyond a certain temperature, although crystallinity has not fallen, right, it can still happen. So, on a tensile property, okay, although we said tenacity of a textured yarn is not so important, but at least you should know what is happening. Okay. So, it is the same kind of temperature range in which we want to work. We were quite sure as to what is the rate of crystallization, which we may, let us say, want to plot. This will be always like this, but let us say I am interested in tenacity. So, what would happen to the tenacity of a textured yarn? We recall crystallization will happen, it gives you stability, rigidity. But what is the texturizing process? And during this process, the textured yarn or the yarn under which is being subjected to heat treatment is not a parallel bundle of filaments. It is not a parallel bundle of filaments. What is it? It is a twisted bundle. So, the texturing is taking place or heat setting is taking place while the yarn is twisted. Now, would you like to say what is the tenacity effect of temperature on tenacity? Yeah? Decrease. All right. Will it be lower than the parent yarn or increase and decrease? What? It will be lower than the parent yarn. So, let us say if the parent yarn tenacity is this, so if we look at the same kind of a range, let us say we are working on a range of this type, because let us say optimization. So, the textured yarn tenacity will be always lower and this will only fall. So, while the crimpacity can increase and come down, the tenacity of the textured yarn will be always lower than the parent yarn, and by increasing the temperature, whatever happens, the crystallinity may be increasing, but the tenacity will go down. So, one thing you probably can now appreciate is that increase in tenacity is not related to tensile strength in a direct manner. Right? If it is not crystalline, it will behave differently, but you can always have a system which is more oriented. So, when we talk about tenacity, it is the orientation of the fiber which is more important, plays important role than the crystallinity, which we have seen now, that the crystallinity could be high, but the tenacity can go down and keep going down, and if you go further and further, it will keep going down further. Molecular degradation, all kinds of other things, fusing of filaments, everything will be responsible for decrease in tenacity. I am not talking about elongation, so you can try and appreciate what will happen to the elongation of the fiber when you are doing all this. So, at kind of a, when you sit down at home and trying to revise, try to see what happens to the elongation of a textured yarn. So, although this does not appear to be very interesting as far as texturing is concerned, but let us say we try to understand what it is. Polyester I have just said for an example. Dispersed dye is another type of a dye. Do you understand what is a dispersed dye? Yes or no? Yes. And a polyester, you understand? The dispersed dye can dye polyester, it can dye nylon, it can dye under difficult acrylics, it can also dye polypropylene under certain circumstances, right? Conditions have to be different. But the important part here is the curve that you have a relationship. If you have dye in solution versus dye in fiber, you are dyeing with the dispersed dye some of these material. Okay. Then we see a curve like this, that there is some space. Obviously, dye cannot go into the crystalline portions. So, there is a space which is the amorphous phase, the dye diffuses in there, and this curve obviously talks about something called a partition coefficient. So, dye in a fiber at an equilibrium will always show this kind of a curve, all right. This is a partition coefficient, or sometimes it is also referred to as solid solution. Okay. So, we will just try to see if we can complete this part today and please get some interesting. Suppose I am interested in plotting, I am doing texturing at different temperatures, and I also want to know what is the dye uptake of a textured yarn. Okay. What do you think would be happening if I have to plot temperature versus dye uptake? What type of curve are we expecting? Increasing and stable. Increasing and stable. Okay. Anybody else? Because let us say have some kind of a discussion. We got 2 more minutes to go. And we did say that the dye will go where? In the amorphous region of the fiber. So, is this curve okay? Yes or no? No? No. So, which is the curve we would like to have? We like to have this curve. Is this okay? No, this is also not okay. Okay. Then what do we have? This curve straight? will this curve be inverse of the crystallinity curve? Yes or no? Inverse of crystallinity? Then why we are saying this is no? All right. So, anyway, you rejected, I am also rejecting. What people see is a curve like this, a curve where the dye uptake is decreasing. Is decreasing because crystallinity is increasing. So, dye uptake is going down. Then there is some kind of a thing which is nothing is changing, more or less, depends on this curve can change a bit of a width and then starts increasing. Interesting? If it is interesting, then we leave it here, and if it is understood, then anyway you will have the answer. If it is not understood, then we will discuss it later. But this is an important observation, and for practical consideration this is going to be interesting. So, let us see if you can find an answer. So, we stop here today.